Yeah. Hello, everybody. Let's begin our second and the first speaker will be Pablo Pérez-González, both about understanding the famous little red dots. We wait for us.
So I think I have heard with this time 4 times the words little red dots together during these almost 3 days. So that's weird for me compared to the last conferences I have attended. So you will hear many more in this talk. And I guess that was the idea of the SOC and Omar when they told me to talk about this topic. So in fact, I'm going to try to summarize in 17 minutes. I have said 157 papers with the words little red dots, but there are like almost 200 in total because there was time they were not called little red dots. In these 3 years of JWST operations, 12 only this month. So there's a huge variety of papers. During lunch, Luis told me that people are very opinionated about the little red dots. They have strong opinions from the very beginning. So I completely agree with that. And in fact, I challenge you to use this URL, url.com, what is an LRD, and vote for what you think is an LRD, maybe before or after the talk, in case I change your mind. And I have some quotes from people from the social credential movie all around my talk. You can read them as we go. Okay. So the history of little red dots, or history of JWST starts on July 12th in the launch of JWST. At that time, the United States had a president that had a value on science. He attended the presentation of birth certificate data. And it was an honor because the war went on and got itself in a hit that target. And in fact, only 13 days after the launch, which in fact is known as 48, which in fact means that there's a big probability on Friday the 22nd, which is 10 days after launch, the first paper appeared, a very famous paper by Lavette, where he talked about some galaxies which had a weird spectral distribution, flat in the UV, and very red in the optical and near infrared. Okay, they were looking for this kind of double break sources with a line break and a bundle break, possibly. And this was a very famous paper. They calculated the stellar masses, and they were looking for this. And they said that these galaxies were very, very massive, even 10 billion solar masses, approaching up to 9, 7, 8. Okay, that was incredible. These were funny sources. And these were how they looked like. 2 of them, in fact, averages 9, averages 7, were in the border of breaking cosmology because they had too many stars, too many variables. Okay, and this was a paper at the end of the month of August, at the beginning of the month of August, so 15 days after the data was released. And here, just a few weeks later, at the end of the month, the controversy started because some people like Ensley said that, okay, you could get the same sources of Lavette fitted with regular star-forming templates and got a very large mass. But if you take into account that they would be stars with a very strong nebulous emission, then the mass goes way down, 2 orders of magnitude. And if these emission lines come from star formation, but only also, or maybe an AGN is also there, then you can have very different masses altogether. So the controversy about the masses of these sources started. Okay, for now they were not called literal dots. A bit later, in October 2022, we got a paper where we selected red sources in general from JWST surveys, and we saw that there was a population of sources here in green in a main sequence plot, okay, very starbursting, that we identified with very strong light emitters. Okay, we call them extreme emission line galaxies of redshift 7 because we thought that we were seeing H alpha notching into emitters going through one of the filters that we use in the selection. Those were exactly the same sources. Okay, but important information, they were just like 10% of the global population of galaxies at redshift above 4 than JWST. So they are not that many. Okay. And in fact, we also obtained this, well, this is a problem with the translation between PowerPoint and Keynote. We also got some fits for some of the sources that Nave had selected but in our fits, we had the strong emission lines and our masses were much lower, 10 or 100 lower, the same as L3, okay. And in fact, some of them, we had different redshifts. This is a source in the Nave paper, redshift 8, we got 5.7, and in fact, this source was the first of this kind that was spectroscopically confirmed. And here, another thing appeared. In this paper by Kochevsky, with this first source of its type with the spectroscopy, we saw a broad component in the H alpha line, implying 2,000 kilometers per second, implying that probably there is an AE. And we calculated the supermassive black hole mass around 10 to the 7 or several times 10 to the 7, depending on the amount of extinction that we assume. From that point, a lot of the spectroscopy started to appear. This is the most famous source of this kind. I don't put them into the dots yet because all these papers came before the name, okay? And this is very famous because it's a triple image in a lens cluster of one of these sources. And this is the spectrum taken with JWST low resolution mode, covering from 0.6 to 5 micron observed, which is the optical and infrared frame. Okay. This paper also about this paper is very interesting. Again, this strange, which what we call V-shape, okay, flat spread. Okay, and since this is a lens source, they calculated a very nice size, and we found that they are very compact, below. Theoretically below 35 parsecs in this case. We go 1 year in advance, okay, not the top name yet. And we come to the culprit of the only guilty man shot. Okay, Mathin is the first one that gave the name to little red dots. The name was circulating around, but he is the first one in this paper. He was looking for galaxies with broad emission lines in recent data from JWST. He was looking at something for 8 and he found them. Okay, he found the same sources. You can see here how they look like. It's the same kind of sources that all the papers that I have told you before. Exactly the same, but now they started to be called little red dots. Okay, but at the same time, that's not exactly the same. These were very few. The ones that Matthew selected were very few among the more larger samples of little red dots that we were selecting in a different way. I will come back to that. There were many more spectroscopic studies, and we saw that all of them had this, all the spectroscopically follow-up sources had these broad emission lines, and some of them is very important, show this self-absorption in some lines. So the emission and then self-absorption in the middle, implying what you both have in mind because you are experts on this. May 2023, we did the first paper with a comprehensive selection of little red dots with photometric approach. Easy peasy Japanese, to just take a color and a band, in this case, 277.4, also another color in the short wavelengths, and then you can isolate these sources, which are very weird because instead of getting red in the optical and UV at the same time, they get red in the optical, but they still are blue in the ultraviolet, which is the V-shaped direction. We discovered at that time that some of them are brown dwarfs. This is V-shaped, but this is fit to a brown dwarf, and in fact it was confirmed with proper motion that is a brown dwarf. 40% of the sources that we select photometrically as little red dots are brown dwarfs. Confirmed. Okay. June 2023, another important date. LaVey strike back and the paper from LaVey I read, but he even didn't reference his first paper, and he made a completely different interpretation. He said that the UV in little red dots is coming from probably the brown line region and the vision this, so typical ADM, and the red is dust storms. Okay, so all ADM dominating. This is he based that on the JWST data, and also on ALMA data. The ALMA data were undetections so very low, so you don't kind of have much dust transformation because you would get much more fluxing, And this is their fit with dust curves model, okay, of an AD. But here, if in order to test whether this model is correct, we can go to even longer values with yellow sheet with here. Okay, and that was our job in January 16, 2024. This is the paper, the plot from LaVey that I have just shown you, and we did a selection of little red dots and a stack of the data. I'm going to pass to this plot from my paper, okay, and this is exactly the same of LaVey, but with many more sources, okay, I started with NIRCam, but this is what Miri told us, that you don't get it up there. So there is not a big dust turbos as what LaVey said, okay. Something else is going on. How he said little red dots are so diffuse. 5 minutes, yeah. With all these sources, now we know that they are typically sources that you don't get little red dots below redshift of 3 or so, very, very rare. The peak is now redshift of 6, 7, okay. I think there could be little red dots beyond that, but probably we'll have to go to Miri to select them, so we haven't done that yet, but we are in the way. More things about little red dots. If they are LGN, we expect some variability, unless some weird things happen. And this is a paper where they claim that there is no variability. This is one epoch, this is another epoch of little red dots, just subtract one from the other, nothing. So no variability. This was the first paper claiming that there is no variability. Now there are papers that claim variability in some little red dots, I would say. Maybe Luis has another opinion, but here, and it's weird because here, for example, in this paper, I don't believe that much because they compare near spectroscopy with imaging, and you have to be very careful in comparing that. In this plot, there is some variability between different, this is the 4 dark little dots, different images of the same source, and you have to be careful with lensing there. And this is another nice paper where they claim that there is some variability, some of them, which will be consistent with large Eddington radio ADN. Okay. In the ADN, you expect X-ray emission. No X-ray emission. You stack sources, and there is nothing. This is all the stacks from all the LaVey sources. No, nothing. Bad luck, I guess. It floats around. There are alternative explanations. If they are something bad, maybe they have a lot of stars in a very small volume. They rotate very quickly, and then you can have this large emission line fluvical maxima. So this is a paper by Wagen where they say that they could be only stars, and then they will have densities similar to global clusters in the lower regions. Two more thoughts about this. The latest mode, because we have like fashions in little red dots, and now the big thing is black hole stars. So some little red dots have a strong Balmer break, so strong that no star or no stellar population can reproduce them. The alternative here is that we have a black hole with an accretion disk and a huge amount of very dense gas around, which is like a star. The gas is heated and it emits nearly like an A star, but with a huge boundary rate. Okay, you can see here the densities that we need, and in the next slide we have here also the data that you need to fit this black hole star model. And there are some of them that look like this. Now, my problem is that they don't fit the mirroring data. These models don't fit the mirroring data systematically. If here, I'm not showing it, but these models don't fit the mirroring data image, so there is something going on. They don't fit the data, and again, they stay high compared to the mirroring data, exactly what happened with the line. So, two more slides. There are some, those models, black models say that there is no data at all, but we detect a few little results, some of them even in incursion. This is one of the two that have detected incursion. They are too high redshift to be detected. But they are important. Little results. If you assume that all little results are alien, this is the luminosity functions that you get at low redshift of 6 or so, and high redshift of 7, and they the luminosity functions are above the ATN, so they would be an important phase in the evolution of supermassive black holes and galaxies in general. And in fact, some little red dots and some ATN that are not little red dots, when we put them in this typical model of supermassive black hole mass versus the stellar mass, this is the local relationship. I extend it to lower values and put all the JWST values. You can see here a lot of galaxies, a lot of them are little red dots that have masses of the supermassive black hole as massive as the stars. These are nearly the 1-1 line. Maybe those are outliers and not reliable, but there are some that have 10% of the mass in the supermassive black hole. That was my last slide before my conclusions. I hope I'm fine to go through them. I'm going to divide them in facts. There is a wide variety of types of little red dots, and in fact, two ways of detecting them: the original Mathy way with the spectroscopy and photometric ways. It matters how we select things. We know that selection effects are important. So I would say that the definition of little red dot is confusion in the community. It's a phase that appears above redshift of 3. It's very important. Above redshift of 7 indicates afterwards. Maybe that's the decay is linked to observations, but it's very important at the first 1 to 2 years of the universe. 20% of little red dots are brown dwarfs. They're very compact. The V-shape. So there's some star formation for sure. Some little red dots show blue things around the red part. So the blue, I think most people agree that comes from stars. In most of them, there are some metals in some of them with the strong breaks. Well, no X-ray, no variability. Well, if you only believe in facts, maybe we should forget about sending more papers about this. But we are astrophysicists. Probably we needed to know what they are. I think there is an heterogeneous population. Maybe you have this black hole star at the beginning, and then you start to get more stars around, and then they dilute the supermassive black hole, and they change in flavor, and that will spend the variety. Maybe they have a massive supermassive black hole. I think we still have to check the stellar mass and supermassive black hole masses. I don't believe that we are doing a good job there. Some of them have dust. I don't know if all of them. Yeah, the temperature could be quite high, and some questions here: what happened to the stars as they evolve, and where, if there are no little red dots below redshift of 3, or they are very rare, what happens to little red dots? Where do they end? And I will stop there. The step that I will, all these questions have no answer. I hope that they will get solved the next time we come to Zihuatanejo. Hope is in the next time. Thank you.
Very nice talk, thanks. Questions? Okay, it's coming.
I remember I haven't seen any radio. I have talked to some people. In radio, and they were preparing a paper with one single detection. That was 2 years ago. I think it hasn't come out, but there is not much cellular detections in radio. But at least one that I know, not published, is there. But we don't have now hundreds much.
I have a question. How do you reconcile this star, black hole star, with a broad line? Because you see broad lines, to every broad line, there is a broad region, how it relates to this dense gas that is all around.
That's a very good question. And in fact, there's a related question that I don't really understand the black hole star completely, because how it differentiates from the classical model with torus maybe only made by gas, an accretion disk. This has to be an accretion disk, but then there is not like an atmosphere. There is a torus. In this case, it would be mostly gas, maybe no dust. If there is not an spherical symmetry, then you can think that you could see some region with very hot dust very near the accretion disk, and then that would give you the. But it's a problem for me also at the very beginning with the LaBelle interpretations, that you could see the broad emission lines, which are not that broad. Normally 2,000 millimeters per second. No. We don't reach 10,000. Of course, the supermassive hole can be not that large, but still 10 to the 7 is quite a number, right? So maybe in that model, it was weird to me that you are seeing the broadline region, but also the dust emission altogether. It goes in the separate direction. But it's true that from the local universe, we all know that there are weird disks in the AGN population. So, and these are weird seeds, probably, of what we are seeing.
Okay. Yes, on my here.
Thank you, Pablo. Good talk. You have demonstrated to be an expert not only in bigger methods but also in social predicts.
You know that why I'm here.
Yeah. Was wondering what kind of models we're going to use, what torus models have been used.
We have not much data for these types of sources to be very careful in what we have done. So in the paper, it was a very simple model. It was Pauletta model, where in my papers I use Pauletta, Sierra Morgan, 2015, not the kind of newest and fastest models that we use in the local universe, but it's true that we don't have the data. But it's true that I think we are shifting towards an interpretation where only some, maybe only a few little dots have dust, and we are seeing the totals. And we are moving more right now, which might be wrong again, to this black hole star model, where most of the surrounding material is gas, dense gas. That's but it's true that the models typically you have to do. You can add dust or not, and we don't know what is the answer. You get a similar answer, but we haven't decided which is the best one. And still, I think maybe a key is to check this data that we saw that it's not reproduced by the models. These three famous statements that I showed.
About X-ray data, which range of X-rays? Because I was wondering if they could be quantum-seeking.
Yeah. But you have to think that the frequency of this is 27, so we don't have a spectral information, but we're always right. And then I remember that maybe I don't know if I have one or two more. Maybe now we can do a better job in other fields, but the ones that have the best data are small and these are not very numerous. So yeah, spectral information in the X-rays should be great, but I think for that we should wait to a future machine.
Okay, we need to move on. Thank you again, Pablo. The next speaker is Andrea Comastri.
Yes, thank you.
The nature of plain ICHM discovered by JWST.
Tell me again. Next one. Okay, so thank you very much. And thank you to Pablo that made much easier my introductory work. And I hope to answer to the very last question in my talk. So the talk is the content of the talk is in a paper which is almost accepted by A&A, and you can find on AstroPH. And okay, so I'm going to talk about James Webb discovered AGN. She has shown in a minute the difference, so I mean the context with the little red dots. So we know that this survey had a very large number of faint AGN with volumetric luminosity towards the low and the distribution, and spanning a broad range of redshift, typically high redshift, but they are found between 2 and infinite in a sense. The space densities of the bona fide AGN are much higher than the extrapolation of the QSO luminosity function, the quasar we know, we have studied, we discovered, we discussed in this conference. And even more interesting, they are much, much higher than the space density of X-ray selected AGN, which typically sample the lower part of the luminosity function, but still they seems to be much higher than the extrapolation of X-ray selected AGN. Most significant fraction of the spectra of the faint UV luminosity show AGN signals. I don't need to repeat what Pablo has already explained much better than I can do now in a few lines. So the point is that not all little red dots, according to my understanding, of course, are AGN, possibly 60%. Not all spectroscopically selected type 1 AGN are little red dot, and type 2 AGN have somehow random colors. So I'm starting with the sample published mainly by Roberto Maiolino and his groups, and they are AGN, type 1 and type 2 according to the width of the lines, of the broad lines, which are not very broad and broadish, say 1,000 kilometers per second or even and around that value. And they are X-ray weak. With very few exceptions, they are undetected in the very deep Chandra fields. And even more interesting, yes, this one. If you stack in the standard band, in the X-ray band, in the X-ray astronomy, we used to stack in the soft 0.5 to 2 kV and dark 2 to 7, so standard fixed band. When you stack, the volumetric correction, or the ratio between volumetric and X-ray luminosity could be as high as 3,000. While this is at the values of the quasars, which we know and which we normally study. And the lower limits on this X-ray, on this volumetric correction are distributed well above the average values of well-known quasars. This is for type 1. So what they are, so this is a cartoon adapted from the Maiolino paper. So this is the SCD and the central region of an AGN with the hot coronal region, the torus, narrow region, and the SCD. So this is our AGN we know. And for the James Webb ISE AGN, we have basically two possibilities, very roughly. Very high obscuration, so maybe there are a lot of clouds in the broadline region or within the broadline region, which are mainly dust-free, but otherwise to explain the X-ray weakness and the presence of broadline. Or they are intrinsically weak. For some reason, the corona or the disk, the accretion disk, is not there and is very weak. And so this is roughly, I mean, just to make a real subdivision. For the X-ray 2 AGN, most of them, only few of them are detected, and interesting enough, a couple of them are very obscured. They are X-ray weak, not as extreme as type 1. This is the same plot, but for the type 2, the volumetric correction of well-known AGN, and the individual upper limit and the stack for the type 2 AGN. If these are obscure, the covering factor is expected to be very high, so in principle close to 4 pi. So what we have done, so a very relatively simple idea, instead of stacking a sample of AGN in the standard bands, we decided to try a rest frame stacking in energy ranges which are not random in a sense, but are customized with the assumption that these objects are really obscured. So we want to sample the SCD in optimal rest frame bands, and after some trials, we decided to use the 1 to 4, 4 to 70, 4 to 7, 10 to 30, soft, medium, hard band. Originally, the idea was to try to detect the stacked signal from strong iron K alpha lines, which are known to be in very bright in the quantum thick AGN. But then, okay, you see, we failed on that. And we only consider type 2 AGN in CDFS and type 1 AGN in CDFS plus CDFN for several reasons, to maximize the product of X-ray exposure and publicly available data. So in X-ray, we have basically two gold fields, which are Chandler's field south, the deepest ever X-ray exposure, 7 megaseconds, and in the north, 2 megaseconds. Coupled with the Chandra spatial resolution, these are the best data we have on the market to go very deep or as deep as possible with the current data. So this is the sample of type 2 AGN. We have 36 objects over the redshift range between 2 and 9 with a median redshift of 4. And okay, this is an image of it's not particularly instructive, but to show you that the green dots, there are no sources detected in the very deep field. They happen to be in the central region, so we are in the most sensitive region of the field. So we collect a total of the equivalent of 200 megasecond stacked exposure. And these are the results. There is no signal in the soft 1 to 4. The energy range are also tuned according to the redshift distribution. There is no detection in the focus in the iron K band medium band, while we got the 3 sigma detection in the rest frame 10 to 30 kb, so in the very ultra hard band, with the significance which is of the order of 3 sigma, and the stacked flux of the order of 1.2 10 times 10 to the minus 17, so just below the formal detection limit of Chandra. And this is not surprising by definition of stacking. You cannot go much lower than the limit of your observation. And these are the simulation, because we, to be sure of our results, we scramble the position of the sources and the ground. We simulate 1,000 times, and none of the simulation retarded the number of counts as we observed. So we can say confidently that we have and if you fit the results of the simulation with the Gaussian, our results are just above 3 sigma. So relatively robust. We did the same exercise for type 1 AGN in the combined field. For some reason, there are no type 2 AGN in CDFN, but we are working to enlarge the sample. So the objects are 36 plus 14 with a median ratio of 5, so there are no big differences. The results are here. There are no detection altogether in none of the bands. We have an exposure of the order of 140 megaseconds, so it's the same order of exposure, and the type 1 remains undetected. So if you compute the average flux and luminosity in the ultra band, and you can in a sense have an SCD, a very rough SCD. So we have a detection in the 10 to 30 band, and then 2 upper limits, which are not extremely constraining, but in the medium and in the soft band. And these are models of a very obscure AGN, almost quantum thick, but not yet, and 2 models of quantum thick AGN. The quantum thick AGN comes in many flavors, depending from the reflection fraction, the geometry, and so on and so forth. The point is that they are relatively bright at 20 kV with respect to peak, and then they drop rapidly at lower energy. And so we can say that the combined detection in the ultra bands and the upper limit in the softer bands are consistent with an intrinsic spectrum in the quantum thick regime. So we cannot compute the limit because we have 3 points. We do not have a spectra, but we can confidently say that the spectrum is 10 to 24 or around that time. And So with this data in answer, we can recompute the volumetric correction and the volumetric X-ray, in this case, to 10 kb luminosity ratio. This is an easy plot, I know. This is the yellow strip is the locus of the points of the volumetric correction for the standard type 1 and type 2 AGN standard quasars that with the clear effect with the luminosity. The higher luminosity, the higher the volumetric correction. And so there are several references to data in the literature to compile this plot. 5 minutes, yes. And so these are our results. If we take face value, the 10 to 30 kb luminosity reported to the converted to the 2 to 10 kb to compare with the other data. And depending from the assumed volumetric correction, these points are still above, but now we have a detection, not a lower limit, above the relation of the well-known of quasars and the type 1 and type 2 AGN. But then if you correct for the absorption, then we were able somehow to constrain this the error are large. These points, assuming, for example, the volumetric correction of Natzer, if you correct, so the data for the type 2 AGN, they nicely fit with the volumetric correction or ratio that we know for standard for obscured AGN. So in a sense, then there are other examples of objects, a lot of details. They cannot go below this line because this would be some physical. The X-ray luminosity is larger than the total volumetric luminosity. So just to give you an idea of the uncertainties in this kind of exercise. But I mean, if you correct the observed X-ray stacked signal with the determined X-ray absorption, they are not very different in a sense from highly obscure AGN. Okay. So another point, this is a little bit technical, but anyhow, it has been claimed that if they are very numerous, up to 100 or this kind of numbers larger than X-ray selected AGN, they could, but being X-ray weak or silent, they should not be a problem for the X-ray background. The X-ray background is made by obscured AGN. If you add a factor 100 of objects and they emit X-ray, you do not fit anymore the X-ray background. If they are X-ray silent, fine, you can put a lot. There are other issues, but you cannot. You have no problem with the fitting of the background. However, our results are telling us that these objects are obscured AGN. So we have to add a so far unknown, a previously unknown population of very obscured AGN with relatively low luminosity. So there might not be infinite freedom to add AGN, obscured AGN, even in the low luminosity part of the luminosity function. Otherwise, you may you are not compliant with the X-ray background spectrum. So in a paper back 10 years ago, we have shown that the XRP uncertainties and the assumption on the geometry and the distribution of very obscure gas, you can still accommodate a factor 4 of evenly obscured AGN in the background without violating its limits. And given the current numbers, we are more or less, we are still well within these constraints. Type 1 AGN remain baffling. They could be either obscured by dust-free gas or intrinsically weak as expected, predicted by some super-electron accretion model recently published by Pacucci and Narayan, Malau and Dart. In the hypothesis of mildly super-electron accretion, the expected X-ray spectrum is very steep, with slope as steep as 4.5 compared to 1.82 of standard AGN. Coronal temperature very low, with temperature below 30 kV to be compared with the 200 kV typical of AGN. And so they have large volumetric correction. With these models, you can still explain the weakness of the observed spectrum of these objects because they are very, very steep and the K correction is working in the opposite direction and you are simply getting a part of the spectrum which is rapidly decreased. Perspective, future perspective. So in the future, in the X-ray future, we have axis and Zihuagn axis is another mission, is a proposal for another mission, which is going to be selected in a few years, assuming that nothing changes. Zihuagn is a excitation, which is on track, hopefully, and so it's going to be adopted soon. And so, I mean, they are from the typical axis surface, it will have a flow fly well within the range of fluxes that we have seen for the brightest sources. We may be lucky with Athena, new Athena, to detect some of them. Just let me remind that I am in the business of X-ray Athena since 25 years, and still there is a long way in front of us, so we have to have a lot of faith and to hope that this Athena will detect will end up happily, in a sense. So these are my concluding remarks. So the starting signal was detected in the ultra band. Type 2 AGN are obscure low luminosity AGN, so there is no great mystery. Type 1 AGN remain still unknown, and in the future we try to enlarge the sample and try to obtain new results. If I have a second, I have my selection of the movie, which is Perfectos Desconocidos, and which is a remake of an Italian movie, Perfetti Sconosciuti. Given that I am an X-ray astronomer, and today at breakfast, a few of you, they asked me, I'm not the conference, I haven't seen you. So just to say that, no, it's okay. I mean, it's perfect. No, it's not my community, but I was very happy to be here, and I find a place in this community as well. So it was a very successful film at the box office, and I hope it's also, and I'm sure it will be also successful. Thank you very much.
So I understand that you have two sources where you get a detection. There is obscure luminosity. For the type 1, you have the one technique. For the type 2s, you should also, but if it's there should also be type 1 equivalents, right? So do these derivatives know type 1 equivalents to the type 2s you detected exist? Because
we have a similar for the sample of type 1 and type 2. The type 2, the static signal of type 2 is there quite from type 1 and type 2. So I don't know this.
But this would imply that in these samples, what we typically say is patient-dependent response in the work.
Yeah, in a sense here. Yeah, that's a good.
Yes, Pablo has question.
So if I understood correctly, you said that with the type 2 there would be a problem with the X-ray background or
Not yet.
Not yet. But your samples will peak average of 4 or 5. So if you want to deliver those the average of 6, 7, 8, 9, then we are in much bigger trouble, or would we say that?
Well,
it
kind of depends. If the luminosity function remains flat about ratio 4 and 5, you can start to enter in a dangerous part of the parameter space because you add the sources. Usually, the luminosity function and high redshift decrease steeply, so there is relatively large freedom to add.
But in other words, the work that you have presented don't account for bigger nodes, which is 6, 7, 8.
Some of them are little nodes, but not.
If you BTC on the population that is 85, do you think these are equivalent maps? Maybe different. Also, in this sense, I know what. And it's really not similar to 19 and we see those data.
see in the acceleration. It is why I'm learning things. What changes? I don't know. They could be. I mean, yeah, I forgot to say that I'm assembling the login. That I'm taking the scale part on the side. Then yes,
Okay, we need to bond. Thank you on there. Yeah, the next speaker is Alberto Rodríguez Ardila. That's going to talk about a novel light mass scaling relation.
Good afternoon, everyone. I'd like to thank the SOC for the opportunity of presenting my work here and study submission. I'm going to work to talk about the novel black hole mass scaling relation based in coronal lines and supported by accretion predictions. This model gave us a very nice review about the scaling relationship for determining black holes in the end. And as we already know, determining the mass of the black hole is one of the most important parameters in the AGN because it brings a lot of physics. However, determining the black hole mass is an easy task. And here I summarize the three main methods currently used for that. In the first case, we have variability. That is a very nice, precise method, but it is very expensive in a certain time because it requires following the source for a very long time, years sometimes. So it can be applied to the only on a very restricted set of sources. We also have the dynamic method that requires resolving the sphere of values of influence in black hole, but in the case of the most massive ones, is on the order of a few parsecs. So it can be applied only to nearby sources. And the third method is the scaling relationship that can be applied to large number of sources. And there are, in fact, unused single input spectra. Right now, there are a lot of scaling relationships in the market. Probably the most, the one that is most utilized, the M sigma, the M sigma relationship. But that requires the measurement of the stellar velocity dispersion of the bulge of the galaxy, and sometimes it's not easy to do that because we don't have access to that component in the given node. We also have other relationships, scaling relationships, like inferring the galaxy size using the hydrogen lines, but even if it cannot be applied to obscure sources or methods based on the oxygen-3 or the iron lines. But in general, when we use emission lines, we also know that the AGN have many other components. We have, for example, a stellar component, a stellar population, and outflow, and stellar outflow. So determining the true component of the AGN in these lines is tricky and not really straightforward. So in this sense, it comes the use of coronal lines because of the high ionization potential that is in the 100-400 electron volts range. It can be attributed only to, it can be used only by a hard continuum, and that the hard X-ray continuum that only AGN has. So if we see a coronal line, we are 1% sure in an AGN that it is produced by the single source. So these coronal lines also are very useful for determining the trace, the shape of the ionizing continuum that has been shown by several authors. And if these lines are photoionized but accretion disk, they can be tested depending on the black hole with the temperature of the disk. Here in this plot, we have the spectrum of MRK 1388, and in red, we have the coronal lines on the near infrared medium. We can see that in some cases, silicon-6, for instance, can be stronger even than the bracket gamma, or in fact, they can be very strong in some sources. Here in this table, I have the coronal lines in the near infrared, and here, very important, the ionization potential, and most importantly, the critical density of the transition. And it can be said, can we see here that all of these lines have very high critical densities. So they can be produced in environments with densities larger than 10 to the 6, 10 to the 7 cubic centimeters. So in principle, it can be produced even closer to the PLR than any other forbidden lines. All these are forbidden lines, of course. So based on this property that these lines are truly indicators on the NGA or the EGA continuum, and they can be used by very large densities. We started a program aiming at determining the black hole mass using these lines. To our goal, we choose a sample of objects from the Spectral database, that is a collection of 86 AGNs where the black hole mass has been measured by the reverberation map. So they have very good determination on the central black hole. And all, of course, they are all type 1 AGNs. And here we selected 31 of these galaxies and obtained optical and near-infrared spectroscopy using a variability of telescopes. Here I have an example of one of the spectrum MRT 1510. This is a type 1, and here in red I have the coronal lines like sulfur 8, silicon 10, and silicon 6. Also here I have another spectrum of 3C120, where we see also this coronal emission in the near infrared. So we tested several combinations, several line ratios, and here I present the results. Here in the y-axis, in all cases, the black hole mass as measured by the reverberation mapping, and in the x-axis, I have a given line ratio. Here, for instance, silicon 6 normalized to the black and gamma flux of the broad component. Here, the silicon 10, the sulfur 8, and the iron 79 in the optical region. In all cases, it is normalized to the flux or the nearest broad hydrogen component line. And here we see that this, in this case, this relation or this plot follows a very close relationship between the mass of the black hole and the line ratio. So if in principle, here for our test, we found a very nice fit with a correlation parameter of 0.8 and a probability of 3.8 times 10 to the 5. So now we wanted to give a meaning to that correlation. So why this correlation shows up? Because it's not simply saying it's correlated and it's okay. So we wanted to explain why this line ratio appears as a suitable indicator of the mass of the black hole. So our starting hypothesis is that if the coronal lines are photoionized by the accretion beats, then a trend between the coronal line strength and the black hole mass may be expected. And this is what we found here. For that reason, we ran a set of cloud models in which our continuous in the standard AGN continuum cloud using 3 different black hole masses. Here, 10 to the 6. Here is faint, but it's 10 to the 7. And in the upper part, 10 to the 8 solar masses. We have two different sets, SMDs for each black hole mass. The dotted line is with a spin, black hole spin of 0.8, and the continuous line is for a spin of 0.99. And it's easy to see here that in the vertical dot lines are the position of the ionization potential of a given line. And you can see that for the lower black hole masses, the shape of the ionizing continuum basically follows all these initial lines. When the mass of the black hole increases, we can see that some of the highest ionization lines are left behind or are not within the LSST, meaning that probably in the spectrum of the sources, these lines will not show up. So also we basically prove the coronal emission as proxy of the temperature of the accretion disk, and we ran several models using this description. We set the clouds at distances between 0.3 and 30 parsecs from the center. This is constrained because 0.3 parsecs is the size of the silicon 6 emission after 35 gravity. And 30 parsecs are usually size of the coronal line region measured by symphony or adaptive optic observation. Also, we tested this density range because 10 to the 4 cubic centimeters is usually a typical density found using the mid-infrared lines, the neon 5 lines, and 10 to the 6 because these lines have a very high typical density. They certainly can be produced at a very high density environment. And the ionization parameter was also varied between -1, 0, and 1. Here is this expression that we employ for the continued emission. This is a standard continuum, the AGN continuum, and for the temperature of the accretion is we form the description of Zihuagn and Zihuagn. So here, for instance, I have the results for the silicon 6 lines, where in the upper part, you see all the results for the spin of 0.8, and in the lower part, the results for the spin of 0.99. Here, in the left, for the distance of 0.3 parsecs, 3 parsecs and 30 parsecs. The points are the observed points, and here we can see that in general, when clouds are about 3 parsecs from the central source, can be reproduced by the set of models. Here, the different colors reflects the density. Red is 10 to the 4, green 10 to the 5, and blue 10 to the 6. So in general, we found out that a very good parameter for the coronal line region are that these lines are produced at a typical distance of 3 parsecs for the central continuum. We also did some, we applied these models to the other line ratios like iron 7. In general, iron 7 didn't show a very good relationship, but still they can be reproduced by our models using the same set of parameters. But for the other higher ionization lines, like for example, silicon 10, we found that the models are not able to reproduce the points because in any case, we didn't have any relationship, any type of relation between the mass of the central black hole and the coronal emission. So in principle, these lines probably are produced in the inner region of the nearline region. So they are not produced at 3 parsecs or probably at distances less than 0.05, 0.1 parsecs from the central source. So, but in general, what we can say is that with silicon 6 emission proves to be a very nice proxy for determining the black hole mass in AGX. And because of this very tight correlation, we continue observing or we obtain a spectral for 15 additional sources from the database, and this is a very spoiler alert. This is our result with the new with additional with additional 15 sources. All the points that we got fall within the limits of the correlation. I didn't mention that the black line is the best fit. Here is the dashed line is for sigma, and the dotted line is to sigma. So in general, we have a very tight relationship and a very easy way to determine the mass of the black hole based using coronal lines. Still, we have more data that should be added here. There are regions that are not very highly populated, and we expect to do that in the future. So I would like to invite to test this correlation, test freely and will, and I will be very happy to have your feedback in order to see if it is indeed useful for that task. And so the final remarks, we report a novel black hole mass scattering relation over almost 3 orders of magnitude for determining the black hole mass in the interval 10 to the 6, 10 to the 8 solar mass and coronal lines. A key parameter driving this correlation is the effective temperature of the accretion disk. This is in line with the thin disk prediction when the temperature of the disk escapes to the mass of the black hole to the -1/4. And the proposed scaling offers an alternative for black hole estimate using single epoch spectra. With James Space Telescope and big surveys in the infrared region, large sample of AGNs equated using this approach. So, and just to finalize, I would like to show you my recommended film, a single film that was produced in 2023, and it's a very, very beautiful film. When a woman married to a former politician during the military dictatorship in Brazil is forced to reinvent herself and show the new course of the family after a violent and arbitrary act. So it's very, very nice acting. It's a quite beautiful film. So thank you very much for your attention. And I'm going to
Yeah, because the information is quite strong. So, I give our or at least please. They say please sign for which shows from and for example, the scene some of these analysis if we are
yeah, it's a very nice question, thank you. And in fact, all the spectrum that we use here are significant. So in principle, we didn't have any data with advanced public, for instance, so that if you have the nuclear spectrum integrated, I think is sufficient for that determination. So the point of the extended emission, although indeed many AGs are already extended emission, this emission is much fainter compared to the emission that comes from the central region. So in principle, it can be contaminated, and that can be explained and scattered in the relationship. But we believe that the extended emission, mostly in type 1 GS, when you observe directly towards the central source, it has no significant effect.
Linear factor or the line or the line dispersion. If we change these parameters, you think that the relationship will be
not at all, because here, the only thing that we have here is just the flux of the emission line of silicon-6, the integrated emission line flux, normalized to the flux of the broad component of hydrogen. So it has nothing to do with the width of the line or whatever. Okay, but this is the black hole mass measured from the variation model. So in principle, it is well. I know that there are a lot of assumptions in the variation model. But in principle, if we took as granted that these determinations are solid, I mean, this is just as a way of calibrating this relationship. So, and obviously, it's posted down on nearby sources. So, in principle, it would be very interesting to use this relationship to add, for instance, and these also are galaxies that are classical sector 1 galaxies. So it would be interesting to add something like dwarf, sector 1, sources that redshifts or something to see if that is in the band. But at least we have calibrated a very nice relationship using nearby sources. So you have nothing to assume about the width of the line or something like that.
I have a question. So the presence of the coronal lines is usually in type 1s.
No. In fact, the studies that we have done shows that it is usually present both in type 1s and type 2s at the similar 50% of AGNs shows coronal lines. The point is that we are first, in order to calibrate this relationship, we needed to use object very robust determination of the black hole mass. But it's also interesting to mention that when we use type 2 sources, the correlation doesn't hold. So we are trying to see why not, probably because the hydrogen is produced in a very large zone. I mean, when you have just a narrow hydrogen component, it is produced from the very inner part of the narrow-line region up to the outskirts of the narrow-line region. So the volume emissivity is much larger than in the case here, than we have hydrogen that is produced in the most central part of the broadline region. So for safest two galaxies, that correlation is not useful.
Okay, let's think of it. The next speaker is Hernández Santisteban. Going to talk about mapping the accretion disk of AGN at high redshifts in LSST.
Thank you, everyone. Yes, I'm Juan Hernández Santisteban. I'm coming from San Luis, coming back to Mexico. Having given a talk at a conference in Mexico in over 15 years. I'm waiting for the opportunity to invite me. So I'm going to go on very small scales of what most people have talked over the last few days. And I'll hopefully try to address these three main points. Whether we are able to solve the accretion AGN, what is the actual geometry? So how does the accretion flow actually look like when we get very close to the black hole? And where does that variability that is ubiquitous among all AGN, what is it actually? So we have been talking a lot about parsec scales over the last few days, but I will be talking instead of parsecs on light days, right? So I'm going to be focusing mostly on the inner part, talking about the accretion disk and the broad lines, and usually these are very, very small scale, right? Just the scales of light days. For people that are working on parsecs every day, this is on the order of milliparsecs of microparsecs, right? So we're going several orders of magnitude down the scale. So this doesn't look great. Anyway, yeah. Anyway, so this is a compilation of actual measurements from one of the physical parallel secret ones. Is this on Keynote or PowerPoint? Oh, we open it in PowerPoint. No PowerPoint there. Okay. Maybe just that moment. Okay. Anyway, what this shows is a little bit of this size loop, right? That all of these points here are actual measurements of the sizes of the dust torus and what's with one, made in the infrared with Matisse and gravity. And now the Far Intrudes has made measurements of the accretion there. So we're talking here on the order of tens of parsecs, here are about 0.1 parsecs. But anyway, resolving all of these structures in AGN, they are unavailable with any current or future instrumentation. They're just too small. So how can we go and measure all of these very, very small regions on AGN? So instead of thinking about size scales, we have to think about time. Right? What we're going to try to do is use the intrinsic nature and variable nature of AGN to probe these very small timescales. So very close to the black hole, you have this coronal region that is emitting high energy photons. These photons travel at the speed of light and intersect the accretion flow at different regions. Now, the accretion disk has a temperature profile which gets hotter as you get close to the black hole. So when these X-rays hit up the outer parts of the accretion disk, they re-emit the variability generated very close to the black hole, but they re-emit it by hitting up the temperature from where they intersect the disk. So what happens is that you observe this variability at essentially in different regions at different wavelengths. So very close in the accretion flow, you will see that the light will primarily come from lower UV regions. and the outer part, the inner parts of the accretion disk will be emitting at lower energies. Now, the interesting thing is that all of these variability, the X-rays and all the UV and optical, under this scenario should be all coordinated, right? They're all being driven by a single driving light curve. So in principle, if you look at wavelength and light curves of different wavelengths, you can cross-correlate them, find a time delay, timeline between them, and that timeline, because the information is traveling in the speed of light, gives you a first order approximation of the size. Right? And if we interpret this as timelines from the accretion disk itself, there's a very tight and easy relationship that actually tells you that this time lag is actually just the measurement between two bands. It's just a very simple function of mass and time, or the black hole mass and time dot. So timelines can even, so measuring this time delay can give you that information. Right. So how we go and do this? So I'm leading a very large collaboration that is performing intensive broadband reverberation mapping with a Stumbridge observatory. It's a very large team across the world, and a lot of the papers lately have been given mostly by early career researchers. So props to all of you. Right. So LCO is a robotic network of telescopes that are spread all around the world, and what we have done is we have selected bright variable AGN. Most of them are super ones. But we have, so we use this distributed network to essentially hammer and observe AGN across 7 or 8 different filters on cadences of between 3 times per day up to 2 every 2 days. So we have what I would argue is the most comprehensive archive of AGN variability ever done. We have been doing this through 4 LCO projects starting almost a decade ago, and I've been leading the last 2 of them. And we're not only observing these AGN for a few times, we're observing them throughout the years. So we have data sets, particularly for some of them, that have 8 different photometric bands for 8 years, 3 times per day. So if you want to study PSDs, you're going to study lags, these are things that you want to do. And here you have my there's a website where I've been compiling all this. If you want to see the libraries, you can just go and look them. And how do they do in practice? So this is just one example from my grad student program. There's a poster outside, you can talk more about that. But it shows just the quality of data. So this is 12% of commentary on very bright AGN across all these 8 different filters. And what you get is this lag distribution of how the lag changes from across the electromagnetic spectrum. So you see that the lags get longer as you go to longer wavelengths, and that is consistent with this reprocessing of photons, of cooler photons on the outer parts of the disk, which are probing farther away distances. So what we have measured and have essentially learned from all of these are there are several things we're not going to concentrate on. The first one is that in all cases where we have measured lags, all of them scale as expected from accretion theory. So all of them, they have a very smooth increase lag samples in the wavelength, and the slope of this is consistent with expectation of just the processing of the accretion disk. However, if you notice, so this is a famous AGN, AGC5548, the expected Eddington ratio that you get, to just speak it straight away, is about Eddington of 1, right? And I think people know that this AGN is clearly not that. And every time when we look at this, it turns out that the lags that we recover are 2 to 4 times larger than we would expect from just simple accretion disk theory. And this is a very nice study compiling all of this. So basically every AGN has longer lags, say just over this. And this is not just done with this technique. It's also observed in microlensing studies with lens AGN. So there are 2 different ways that show the same result. We just published a paper where we show that maybe obscuration has something to do with it. but it's a small sample here, but there might be other explanations. However, whether you believe that the lags are larger or smaller, they're consistent or not with just a single test, the fact is that what we observe is not just a smooth, simple polygon predicted just by your zero order black body from your accretions. In fact, one of the first surveys just done with Swift clearly shows that in some particular bands, there are deviations from a smooth power, right? Maybe not convincing enough for you, but let's concentrate on this one over here, 4593. Because in 2016, Kakek and collaborators went and did it with HC. Instead of doing it with broadband reverberation mapping, they went and took the Spectral with HC every day for around 20 days. So then you can really see the whole continuum and remove the emission lines and just really trace the continuum. And what they saw is exactly this edge, which in broadband photometry shows as just a slight deviation from the power. This edge is located exactly at the Balmer edge, right? So that's and we interpret this as hydrogen Balmer edge emission, right? So the main interpretation is that what we're seeing here is that not this is only reverberating, but it's actually the BLR as well. We often forget because we focus a lot on the emission lines, right? But if you have emission lines, you also have continuum that is emitting from that BLR as well. It has free and free bound emission. And that emission is polluting all the wavelengths across the UV all the way to the near infrared. And because that diffuse continuum emission from the BLR has very long lag, but it's not that prevalent in the spectrum, it just increases slightly the lags that we observe. All right, so this is what Zihuagn can do in the local universe. But I'm interested in what will eventually become the best laboratory to perform this kind of studies, which is going to be LSST. So can we do this at high redshift? So this is the distribution of sources that we do with LCO, which are all bright, and will still be very bright for LSST. LSST won't be able to do the local universe with it. So we'll still, if we want to do the local universe, we're going to need smaller telescopes than LSST. And LSST, however, will probe these very high redshift from version 1 to version 2 and probably even more. And between LCO and LSST, just here, just show the quasars and the SDSS proxy for the LSST. They're actually probing two different types of populations, right? So between the two surveys, you can actually probe 5 orders of magnitude in mass and luminosity between them. But can we measure lags? Because there's no data yet for LSST, I found that there is from the dark energy survey, it's like they have a couple of papers that they show very similar data what LSST will probably do over the next few years. So I downloaded the data of 30 of photometric data from 36 spectroscopically confirmed AGN, but they cover a range from 0.7 to version 2 all the way to positive. So even though they were taking over 3 or 5 years, in the rest frame, it's just a little bit over a year, or maybe 2 years. So these are very analog experiments of what we're doing in the local universe, right? Just done with this. And like, even in the cadences, even though they're taking it maybe 7 or 10 days across, on the rest frame, there is cadences of 2 or 3 days, right? So they're still very intensive, even though they're at high redshift. So what I did, I used this code that we're developing that's called Pyro, that essentially fits all the bands simultaneously. And this uses there was an equation here, a very linear equation. But essentially what it does is that you construct a driving light curve from all of the data. And it's a linear combination of a variable component that is variable plus a constant factor. And when you do that, you combine the power of all the data together into a single driving light curve and allows you to measure the lags a lot better than if you just do simple cross-correlation functions. And to prove that, these are the lags that I recovered against the published data, that data set that they published a few years ago. So in 31 of the 36 AGNs that were there, I found robust detections of these lags. Right? This is the data that they show. So they barely, like most of the AGMs they have are consistent with no lag at all, but the lags are there. And also for free, because of this linear decomposition, we also get the spectrum of the variable component. And so that means that you have two dependent tests of accretion theory. You have this size and you have the SCD. And these are all the SCDs. And if we compile them together, we show the disk sizes for all of these AGM, and we show the slopes on the UV optical restaurant of AGM. And it turns out that most of these slopes are actually just consistent with Shakur-Sugya approximation. Right? They're all just very blue AGM. There's no deviation. Most of them are just. There's a few outliers which seem to be a little bit better. There may be some host dust extinction, which have been accounted for, but most of them are just blue enough without any additional correction. All right. Are these things larger than expected? And I caution not to interpret this. And I don't make any claims in some paper I just submitted last week. Because we have to be careful that the DCE from the VNR is contaminating all of these bands, right? And this is something that many people just disregard in the literature. These sizes are larger because there's a contamination in it. So if we want to get real sizes of this, we need to remove them. And just to show you that even on for example, one sticky one, a very high Eddington AGM, there's probably going to be finding a lot of them in the high redshift just because of selection biases. We also find that there is a U-band exit. There's evidence that the VLR in 161 is still contributing to the last. So we need to get rid of this VLR contamination. And also because of the small bands that LSST are going to be probing, they're basically going to be probing only the UV resistant. So there's also the worry that you can over-interpret the data because of the short waiting range that you cover. And this is something that González in 2023, when they published only UV data, they come up with an interpretation of the very weird geometry. At the moment that you move the optical bands, it just loses as any other AGM. So finally, my takeaway point is that yes, we can resolve the accretion disk on AGM. We can resolve already on milli and microparsec scales. And 1 meter telescopes, most of these data is done with 1 meter telescopes. They are powerful if they are used correctly. If they are used correctly. What is the accretion post geometry? We still don't know. I think there's still an open question whether there's a wind, if there's a wind in the AGN, where is that wind coming from? Because all of these pictures can be tested with this technique. So what we need to do is to create this template, and I have an HST program coming up next year that hopefully we'll be able to do that, to create it. And then just to say that this Roadrunner reverberation mapping has already explained, I think Panda showed even something even at 2.6, something like that. But the doing reverberation mapping and plus already exists. The data has been there for about 5 years. So LSST is just gonna explode this field. Thank you very much.
Wonderful synthesis. 2 comments. First on the DC component side of this. Indeed, that the campaign has been built up using the NDC to define what it. Of course, a lot of things need to be updated if you are going to do resources that we should raise. Effectively, need to have that campaign really built up for DCEs. And not only just the background, algorithm and actually done, you're also looking at the helium and ionization fronts in property plants, especially when you go into the swim fishing. That's something very nice to do. The second thing with the LSST, I think most of these cases that we're expecting of 2 days, something that we may only end up in the end, the 60 review. Most likely for the main surveys, it would be very tricky because the cases that would be much worse the other 5 days or longer.
Right. So yes. But remember that those 2-3 days, it's on the rest rate. right? But it's on the redshift, right? So if you've already gone to redshift of 2, that's you're already talking about making cadences, right? So yes, in the deep drilling fields, you will have thousands of quasars where you can do this, and you might be able to get something out of the other like medium fields.
Perfect. And I can just add, there will be an issue with the UMass network. It's not going to be on that slope as often like the other mass. So it's going to be still picking the Y and the UMass. It's not basically being in the.
So I think the important one is going to be the Y band, because the DCE, if DCE is present everywhere, you would expect that the lag should just come down the Y band, and that will allow you to anchor where that other edge is. So if you don't have that number wavelength, or better yet, near infrared photometry that accompanies those fields, which I haven't really heard a lot of. If anybody has planned to do near infrared monitoring of many of these fields, it would be very interesting to talk to you. But I think that would be necessary to complement this.
I have a question. When you talk about the broadline region contamination, this would be the emission lines or the continuum from contamination?
It's both.
Both the continuum and the emission.
Yes, because when you take the broadband, you're just getting an average measurement from that. So all the BLR being first order, they both have the same lab. They're all maybe roughly around the same region, right? But it's producing both the lines and the continuum. I mean, this broadband they just won't just blend together. No? In fact, in many of the very high quality ones that we have, we see that the R band is actually shifted up. And that's because of the H alpha. That's because of the H alpha. So you can actually measure, there's some information about the H alpha BLR line combined there. So, but if you just use everything blindly without taking into account, you can get misguided into measuring all these larger disks.
Yeah.
So my question is, if it is that the BLR is not biggerless, can we still use for the configuration method?
That's a good question. Well, at the moment, I think all the models that we have done imply, at least we modeled it as clear lines. It's just an easier way. And I think at least from the safer ones that we have used, I think there's good evidence that all that material is clear lines. But if that's not the case, then you cannot maybe assume that all the BLR or maybe like your velocity distribution comes from different. But that's going to be harder to extract from the photometry itself. At that point, you're going to need to do spectroscopy or time resolved line velocity resolved flags on emission lines to actually determine whether the gas is realized.
Okay, let's start again.
Thank you.
Sorry, it doesn't for those people who will they always stop and need to leave now. With the head.
Yeah, next speaker is Iliana Cortés. She's going to talk about the photometric decomposition of the gene variability via machine learning. Okay.
Sorry, I was about to say. So, good afternoon, everyone. My name is Iliana Cortés. I work as a PhD student in the Harvard Institute for Theoretical Studies. And thank you for being here. It's the last one of our long day. Can everyone hear me? Yes. Okay. So, the advantage of being the last one is that I don't have to convince you that modeling the global region is actually not an easy task, right? So we have, of course, theoretical challenges as well as observational ones. From the theoretical aspect, we need models of RNAs and variability. It's not useful for us if we have a model with 1 million parameters if we cannot make anything out of it. But at the same time, we need these models to be flexible enough, so we can actually repeat our data. And of course, there is trade-off between those two. But in an ideal case, we would like to have both at the same time. But I came to Mexico not only because of AGS, I came also for the food. So let's imagine something. I give the task of cooking camarones a la diabla, which is spicy shrimps, a typical Mexican dish from the coast. If you haven't tried this, I recommend you to do it all at your own risk. And okay, so I give you this task to cook pictures, right? And then I'm sure the room is going to be divided into parts. People who are going to look at the recipe and are going to follow it to the dots, and people who are just going to follow the reference. And exactly the same thing happens with regression, right? We can follow a given recipe and make parametric regression, or say we want to make non-parametric regression. Right? Both have advantages and disadvantages. If we go for a parametric regression, of course, making an interpretation is going to be easier. But if we make non-parametric regression, then this is going to be very likely a flexible one. Since I'm sure everyone is very well acquainted with the parametric case, I would like to make a start and give you a flavor here about non-parametric regression. Specifically about the case of Gaussian processes. So rather than finding the least function, we are interested in finding the function values at certain given points. So a Gaussian process defines a probability distribution over possible functions. We're not finding parameters, but possible functions. So this is a toy example. And let's think that these purple dots are our observations. And then the gray dashed line is the true target function. A Gaussian process is a stochastic process, so it's a set of random variables, where each variable defines a dimension in a multivariate Gaussian distribution. So that's a lot of words. So let's think of it, the easiest case. We have two observations here. Then the multivariate Gaussian distribution, of course, is going to be a two-Gaussian. The goal of the Gaussian process is to learn the underlying Gaussian distribution, or how these two observations covariate between them. So, to treat this regression, we're going to think of typical Bayesian first. So we choose our prior distribution, and then the idea is to update this hypothesis with our observations, or as we call it in machine learning, our training data. After the observations have been done, then we get our posterior distributions, and a Gaussian process just goes down to draw examples out of its posterior distribution. So we get a mean function, and then we get also a covariance in our functions. That's the rough idea. So, what do we want to do with this and AGS? Our approach is to perform a Gaussian cluster regression on photometric libraries of AGS, of course. And at the same time, we want to use an empirical spectral model to for the problem division and the machines. This is going to because somehow both the flexibility and interpretability. And with this, we want to calculate the time delay between the problem division and equation this, plus to perform spectral reconstruction. So I'm going to present you the toy model, like the easiest possible model for this case. So we start with an accretion disk continuum given by the orbital. And then we add some simple emission lines from the problem region. And we know that over time, this is not going to be the same, right? We're going to observe variability. And as I said before, modeling this is quite hard. So we said, let's go for the easiest way to get it. we're going to treat these late variability as a Gaussian resistance. So we say, okay, definition this continuum presents some temporal functions, temporal variability, sorry, that we're going to model as a Gaussian process. And then we know that the Bromley region lines are going to also present variability function with a time limit. So we use the same Gaussian process for both accretion disk and Bromley region, and the difference is the time limit. And here I'm showing you how these two functions look like. And of course, this is the total variabilities. So we create first medium of photometry by folding our spectral temporal model with a set of photometric features. For this case, we're using the LSST features, and we obtain our. So this is our idea. Our photometry is going to be the folding of the transmission curves with an accretion disk continuum multiplied by the Gaussian process plus the Bromley region emission lines with the Gaussian process, but as a late version. And for this, we need a single spectrum to retrieve the spectral parameters, in this case. The amplitude of, the slope of the power of the emission disk, and the central wavelength of our emissions. And of course, we're in the energy. So this is our results, our raw data. In here, you see only 3 bands, the UGR bands, and this is only for visualization purposes. So we have what you're seeing here is data, remote data, noiseless in this case, and then these different colors, the Gaussian process regressions. With these, we reconstruct noiseless spectra, and we reconstructed latency. And now the more interesting case. We took the regression mapping dataset because they sampled, if I remember correctly, around 900 sources with 90 errors or so. So this is an example for one of projects. And what we did was to split our dataset. We did randomly one spectrum, and then the rest of the dataset was split between 25% for testing and 75% for training. We took our very naive spectrum model, we fitted it with a measure with a regression to our single element spectrum. We retrieved our spectral parameters, and then we created a photometry. We're using only 3 bands because, as you can see, only these 3 standard bands have the wavelength range of the spectrum. We added some noise, Gaussians, and then this was the result of the Gaussian processing. So you're seeing here that we separate the emission disk continuum with the worldwide region emission. And of course, if you see here, this is a very small fraction of the total emission. And that's why it's complicated. This is also it's numerically complicated. But yes, so this is for the 3 central ones. And this was the latency node that is driving the variability in our node. In here, we're still studying these things because at least for some objects, for this one in particular, directions with banks of the station. But these things we believe are more numerical. But we were actually able to reconstruct spectrum. So what you're seeing here, the pink line are observations, and then our reconstruction with our polynomials. This is interesting because these observed spectra know absolutely nothing of our regression. These types were not included in our field. So it was actually interesting that with our very early SQL, we were able to reconstruct it. In this case, for example, it is a bit overestimated, but we're not too worried in that case. Yes, and as a byproduct, calculating the variability. So we're not doing it line by line, only because of simplicity and computational time, but we're already working on that part. And when we compare these results to the RN data, we see that for at least for line RO8, we have somewhat similar results, which was, to be honest, also surprising for me because this is a very, very specific one. And the thing is that for now, our observations are restricted to our live search, which is the category that we're smartly choosing. So we still need to perform NCMC for obtaining a better observe this, but we're hopeful in that regard. So what we're doing now is, of course, working with more complex topics. Because as you heard before, simple models are not enough anymore. But we're using this as a primer to be sure that we can do this step into more complex and realistic physical models that our basis is solved. Of course, we're interested in new surveys. We use the RNN dataset because we know the ground truth for our spectrum. But we're aiming, of course, over LSST because that's the most interesting idea. And as I said before, with the MCMC uncertainties and as a negative message, talking with computer scientists once in a while really makes up. So for my movie recommendation, I felt compelled to put artificial intelligence here, but I'm Mexican, so I think this is a great movie. Pedro Páramo is from 1967. It's I cannot say anything about the plot without giving you spoilers. But it's a very good movie, and it's based on a book by Juan Hernández. It's also a great book, and it's very small. So if you have the chance to read it, I highly recommend it. And it's good to get in the mood if you like to look around the other disciplines. So thank you. I really hope to take your questions.
Questions next.
Yeah, you show like UV spectrum, but usually with the time background, we can have, for example, the index of the radiation pressure. So usually the most safest thing is try to use HV that, like to determine the time lag in this type of model, I can guess that's in that. So why are we not using the optical spectrum? Because also in the relation of the sample there are optical data there. Why did you prefer to use UV data?
We are using also optical spectrum. It's just because this is from the same data set, but we are using the optical spectrum. And I just randomly chose a case, and it was not the best one, but yes, we are actually using the optical.
I'm just curious about the procedure of the VLAN delays. How does your distribution?
The procedure of
your VLAN delays. How does your posterior distribution work?
Okay, that is a tricky question. But this actually, I think, for this case, I can show you later because I don't have to say something that I'm not remembering correctly. But once we got it numerically stable, was great. No, I don't want to say it's actually like it's not right.
Back there.
I just had a question. One of the arguments this would be your assistant to be something that's really good. It's something so do you mind if you are still like the other evidence like system to be something that something? Or do you find it listening this impacts?
It's very hard to be here in front. I don't know if you mind coming here.
No, I just wondering if you find that you're less sensitive to like the cadence of sampling than the other techniques where there's only variables.
Okay, yeah, that's actually an interesting question, and no. You avoid overfitting. So the guidance and the sampling of the data becomes not irrelevant, of course, but it takes a bit less importance than other methods. So yes, that's it.
More questions? Okay. Oh, there is one. Okay, sorry.
Thank you. So the lab that you have, let's see, for the council, it's very simple. Like it's in principle already there might be items lab will continue. So have you tested whether like this model can, because basically you need every single wave has to that it gets propagated in larger. Have you tried or are you thinking about doing this like more relatively related than just simple single math and distant single math for all the elements?
In like function.
Yes, so basically every lab has a different, every line has a different line, and every wave continuum has a different line.
So now we can transfer shift with this, and that was complicated. So yes, in the sense of complexity for blacks, that is right now for the best shot. But we are still, for this time model, we're still working on actually making a lag for each line, because for this one, we're using one single parameter out of lag for all lines. So making it for the three of them, for the programming part, is trivial, but for the numerical side, it's not. So we're dealing with that part, yes, too. So, thank you.
Okay, don't have much more questions. Let's thank Iliana again. Part. In the last session. I mean, I can yeah.